Now, we start on a new section in our lectures. Until now, I've given you the general layout. How to design a bridge in the final stage. That was in the 7th semester. How to calculate the forces approximately. Then I've shown you an overall view how to build the bridge with some hints on construction engineering. Now, all this, in a way, I want to summarize by showing the actual, mainly construction of bridges. There, I hope you will frequently have the feeling, how do we say that? Déjà vu, I only know, in French. In German we say ein Aha-Erlebnis, so that you recognize, oh yes, I've heard this and that. So all these pieces I've tried to line out to you then come together in the actual design and construction of examples. And I've chosen an example for every type of cable-stayed bridges. Concrete precast, concrete cast in place, steel, composite, and series of cable-stayed bridges. And I've chosen either those bridges I've designed and done myself, there I have the pictures, or my good friends have sent me their pictures for their world record bridges. We start what is still the world record bridge, to the best of my knowledge, for precast concrete, the Pesco-Kennewick Bridge, which was my first cable-stayed bridge. I was completely responsible because I was alone in the United States and I had nobody to ask, so I had to think it up myself. So, precast elements. And there is, after the Pesco-Kennewick, I did another one in the US, East Huntington, where I just show some different items. The Pesco-Kennewick Bridge is located in the state of Washington, not Washington, D.C. I always say top left corner of the US map. Seattle is the city which is close, and there's the Columbia River, which runs into the Pacific, major river. And by the way, here we see Tacoma. Here we see Seattle, and here's Tacoma. As you should maybe remember, I've shown you in the dynamic lecture the movie where the Tacoma Bridge is destroyed by wind, and that is here. Tacoma is rather close. At that time, there was no computer visualizations. We started 1973-74 with that thing. So we still had the good method to have an artisan who built a beautiful model, and we took pictures and tried to sell our design idea. That's today not done, but at that time was very typical. So that's a real model, about 1.5 meters long, and photographed. The bridge itself, it's hard to read, I know, has a main span of, I say, 300 meters. It was 1,000-something feet, but we designed all that, of course, in feet and inches. But 300 meters is good enough for precast. At that time, it was world record for a concrete cable-stayed bridge by itself. Today, there are, of course, longer spans, but it's still, with a heavy precast, I think it's still the record. We have a simple tower with vertical legs and a strut. Now, at this place, we have the so-called hold-down piers, very important, because the most important cables, the backstay cables, which govern all the behavior of the bridge are vertically anchored here. The horizontal component goes into the beam, but the uplift forces go into the hold down pier. And the problem is that we have to combine the vertical force to take up the vertical force with horizontal movement of the beam. We have in this case the fixed point here. Okay, there's no horizontal movement. But here we have 500 meters of concrete bridge beam which moves back and forth, and there we had to think up something. Now, we have used post-tensioning strands to stress the beam down. There's a bearing which is always under pressure. Otherwise, if you don't have that, you may have uplift or downlift forces depending where the life load is. So we have always compression in the bearing because we stress it down. And how do we deal with the movements? Now, the movements have two results. The movements on one hand, longitudinally, try to elongate this hold down, and in order to avoid that, we have used here a sliding joint in the middle where it can elongate. And secondly, if we have a fixed cable and move it, I've shown you the second order theory in the first lectures, then very high stresses from second order theory occur. So we must prevent that there is a kink in the cable, and therefore we have used stiff steel pipes here, and we have placed the bearing on a sliding surface, and so it's forced by the strong steel pipes and the sliding here that we always have a rectangle between the hold down and the anchor head, and there is no kink, sharp kink, which could cause breaking. Very briefly, you know the forces in the bridge. We've dealt that in detail. We have here the loads, we have the post-tensioning. So in the end, we have here the run of normal forces from inclined cables and post-tensioning. There's a second order theory. We've gone through all that. Now, Tacoma is close to this bridge site, and people were aware and said, oh, world record and cable stayed, never heard of that, that's new, was the first cable stayed bridge in the US. So we looked very carefully in aerodynamic stability. And so, first of all, there were wind tunnel tests done for the cross-section where we wanted to find the horizontal drag, the vertical lift, and the rotational torsional coefficient depending on the angle of attack. It's pretty normal, nothing spectacular, but we need, of course, these values to calculate the stresses or the moments in the beam from wind transversely. So that were wind tunnel tests done. This is a visualization, I think, with smoke. This is our model in the wind tunnel, and we can see here vortices. It's an open cross-section forming, and we see the vortices forming here. Now, this is an interesting figure I'd like to explain a little bit more. Naturally, you know all about aerodynamics of bridge beams, because I've given you 2 lectures on that. You may recall we have 2 phenomena. The one is flutter, what Tacoma went down with. So, and the other is vortex shedding, where these vortices form behind the bridge and act forces, and if it's in resonance with the eigenfrequencies, it can go up. And we have here the wind speed. The design wind speed was 160 kilometers per hour, the design wind speed. That's the design speed here. And we have here shown, so for horizontal wind, no angle, then this is the wind speed. However, there are very many measurements. When the wind is inclined, the wind speed drops down. The maximum wind speed for horizontal wind, I think that you can easily understand that, is bigger than if I have a strongly inclined wind, the wind speed is smaller. So we have these limits established for the actual wind speed. The full for the horizontal and here for the inclined. And then we see that above these limits, our flutter set on is outside. The earliest was about 170 kilometers per hour, but for an angle of -8 degrees, where we have very little wind. So it's safely outside, that's flutter. And then the other is vortex shedding, which traditionally occurs at low wind speeds, but also, although it occurred at low wind speeds, it was beyond the wind limit because it occurred only at steep inclinations of 8 degrees. So with this picture, we could convince everybody who, not knowing anything about aerodynamic stabilities, just showing, look, all these phenomena are outside our limits, hook it off, well done. So that was how we convinced our client that this is safe. Then you all may know that in California we have the San Andreas Fault, and there's a big danger of a very heavy earthquake. So bridges are now in San Francisco refurbished and all sorts. Now the Pesco Canyon, let me go back. Here comes Oregon, and then comes California Baja until down here. Now we are quite a bit removed from the Andreas Fault and all that, but still earthquake danger, which is stated in the codes. H2 gives certain acceleration. So what to do against earthquake? And at that time the computers were not so good in doing dynamics, 74, 75. So we said we do it by structural device, and we used a concept to have a big difference between the eigenfrequencies of our bridge and the short eigenfrequencies of an expected earthquake. Now in buildings it's partly done that you use a so-called soft story concept, that you have one story without bracing. So this has a very low eigenfrequency. Or you can put a building on rollers, bearings, it has a low eigenfrequency. And we said we choose the way that we install what we call desired failure joints, Sollbruchstellen. Desired failure joints. So what we did at the fixed point, we had a dowel which had a saw cut, quite partly through, and for the design earthquake that would shear away. So we would then have a very 6-7 seconds eigenfrequency of the beam once the fixed point was released, and by that it was rather insensitive, the beam, against the quick earthquake movements. And of course you need the same in transverse direction. Now we have here the tower, that's the beam, and we have here just bumpers, puffer, where the bridge under regular conditions from wind can push against. And these bolts here were very thin and designed to shear off once an earthquake would create heavy transverse forces. So longitudinally and transversely, very high eigenmodes and insensitive against earthquake. Construction, we have a steel tower head on top of a concrete tower with 3 layers of cables. We wanted to come very close to the fan arrangement. And the concrete was built cast in place with jumping forms, as we can see. Here we see already the formwork for the starter piece of the beam. The tower, as I say, we had 3 stay cables, one beside the other, and they were delivered in 3 slices, I may say, pieces, lifted up by crane, installed. The cables here are already in, and then the concrete tower was continued up around these steel boxes. We used to call them concrete ears, where we have the steel part is our head and the concrete ears a little bit bigger, make it composite with the tower. The beam was on one hand aerodynamically shaped. First of all, this was basically designed by Professor Leonhardt himself, which we then realized. Low deck depths, 2.2 meters if I see it right, for 300, so it's 101 and 140, which at that time, that was early 70s, was rather low. You remember Helgeland, we later went to 1 in 350, but this was one step there. And we have here these outside aerodynamically shaped, but there is no bottom slab because it is not required, and it was always an idea of Leonhardt that you could do it without bottom slab, no box section here. It worked. It's not ideal. You have a little problem here at these points to get the stresses okay, but it works. And at that time, very early on, we took we had the joints cast against one another. I mentioned that, match cast, and the shear transfer. We at that time said, okay, we do it by steel. We have some dowels, steel dowels, put into the two which can take all the shear, put the reinforcement to take it up. Later on, we'll see an example, then we just profile the concrete, do away with the steel concentrated shear transfer. But it's, good God, it's nearly 40 years ago, 35 years ago we did it, and there it was not so well known. So here we have then the starter piece of the beam, cast in place concrete. This is a very slice, the first precast element, because here we have from behind we have to cast against, but here we have to glue the first precast elements against. So you have to do an intermediate piece. Casting of the precast elements, I've shown you many repetitions, so we have steel forms. We cast the next one against the end of the one before. So match casting, we ascertain a perfect fit. We lift them up with a portal crane, transport them to the water. We had to do free cantilevering from both sides outwards at the same time. So 270 ton weight elements with a big lever arm was too much for the tower, so we had to stay the tower. I've given you some calculations how to design these auxiliary stays. We close at the side span, then we go on to the center, change to the other side, close it. And we have these auxiliary stays we tie to the cross beam of the tower temporarily with some post-tensioning bars. Now, in the final stage, the fixed point is here. But during construction, naturally, the fixed point here doesn't help us. So during construction, we need a temporary fixed point. And there, naturally, we use the tower. And if that's the beam in the final stage, free to move, we install here a precast element. That's a in plan view, we look down, that's the tower cross-section, and we stress a precast concrete piece against the beam with some rubber bearings here, so we have a temporary fixed point until we reach the final fixed point. Very typical for all cable stayed bridge construction. Here, during construction, we see here the final cables, and we see here an auxiliary cable. Now, first element is precast, lifted up by a portal crane, brought to water on a barge, and up we go. And here it is. It was a great big moment at that time for all of us, seeing the first element going up. It was transported, as I mentioned, to site on barges, and we see here the full system, but I think we have a better picture. Let me just see. No, we don't. Basically, we have here the traveler with some hydraulic equipment here to lift up the 270 tons, and the traveler is tied back to the tower itself because the 270 tons could not be taken by the beam without auxiliary support. And then we have here our auxiliary stays for the towers. So it's a little bit involved, but we had to design all that ourselves because there was nobody in the US who had ever done that. So we had to do that and design that also. And basically, our traveler is a box girder, which is anchored to the beam here because of the horizontal cable component of the big compression in here. These are the hydraulic jacks. That's a new element being pulled up. And this is a auxiliary tieback to take off the load of the traveler from the permanent beam. And here we see a cable guide. Once the element is installed, we pull up the stay cables here, pull up and install. And there's a hydraulic jack at the bottom here with which we, after the element is in, can move forward and do the next one. Looks a little bit complicated, is it? But it worked very well. We see here an element being lifted up and aligned so that it fits the formerly installed. And then we have to do two things. We see here the installed and the new one. We have to trowel the concrete surface with epoxy resin. So it's covered both sides thickly with epoxy resin. And then we have here some post-tensioning bars in empty ducts going through, and at the tip we stress them, these bars, and by stressing them in a prescribed manner we pull together the two precast elements, and we have a certain minimum compression uniform over this, say, epoxy glued area so that the epoxy hardens under small compression, which is the ideal one. All this worked very well. We didn't have to change any direction with shims or something. Later on, people said, well, this epoxy and all that, that's expensive, especially the French. Jean Muller, for example, my friend, built the key bridges in precast elements, match cast, without epoxy. Said, what? Epoxy, we don't need it. Theoretically, yes, but I've been in key bridges and others, and sometimes you can see the sun look through the joints where they do not fit as tightly, which means the water's running through. And so I still insist, use the epoxy. It costs a little more, but it seals your joint. There's always 0.5 millimeter and 1 millimeter, and you have it real tight. So there's a discussion in between people. I think I always would use epoxy, but you can do it without. Well, then we come to the overall picture, the free cantilevering to both sides. We have our two travelers, we have the auxiliary stays, we have the auxiliary tiebacks, and the thing goes on until we reach the side span joint. Now here, which is closed, similar as in the center, I'll show you later. And then of course we have already done something, because then the tower is not freestanding anymore, but is tied back. So that's the first step. And then we do it on the other side the same, and finally then we have the lifting of the last element here. And what remains is a joint. You can do precast joints all the way, but you cannot do the very last one. You will not be able to fit in on a millimeter precast elements in between. No way. So that has to be cast in place. And we had designed the traveler from the very beginning in such way that we could stress the main part, the box, over the joint, because you need to use them as a splinter, eine Schiene, like for a broken leg, to fix the joint, because it works. Temperature, wind, and so on, and if you want to cure the concrete, it must be absolutely without any movement. So we fixed the joint with bridging it and stressing the travelers on top, cast it, and then we have overlapping post-tensioning and reinforcement, and that was it. I mentioned to you that we have change of fixed points. In the very end, that's a fixed point, and all movement goes to the fixed point. However, when we start, there's no connection. We have a fixed point here and a fixed point there. And so the shrinkage and creep moves temporarily in this direction. Then we close the side spans. We have a permanent fixed point here, it moves there. We have a temporary fixed point here, it moves there, and goes on. And all this has carefully to be added up so that you end up with exactly the bridge you want, taking into account the various movements due to change of fixed anchorage, typical for all bridges. Also, in the final stage, after joint closure, what happens from shrinkage and creep? Well, basically, we have a deflection of about 15 centimeters, which of course does not take place by this, but we super elevate the beam by 15 centimeters. We build it negatively this too high, so that at the end of shrinkage and creep, it's there where it shall be. That's what we call shop form for steel bridges which are built in shop. The steel elements are cut to size so that you build differently in that way, that after everything is installed and shrinkage and creep or whatever happens, then it comes down. But it shows it's 15 centimeters vertical movement due to shrinkage and creep is more than for a regular bridge. It's quite something. All this naturally has to be calculated. Now, stay cables. We used high-M stay cables. I told you all about it. Basically, it's a steel anchor head. The wires protrude and they are fixed with steel balls and epoxy. Cold casting, higher fatigue strength than the hot casting used for the lock coil ropes, where we have the zinc alloy with 420 degrees, which changes the steel, and we have a lower fatigue range. The pipe itself, we have the steel wires, 1/4 inch, 6 millimeters. Inside a PE pipe, we have a helical spacer which keeps the wires in place. And it's empty initially when it comes from the shop. Then we have to grout it. And we anchor it here at the bottom by a cast-in steel pipe, anchor head through, and we have the shims or washers stuck in so that they remain in place. All very typical. Now, installing the cables, we used what I prefer to call a high line, which is called here a guide rope, which is installed first, and then the new cable is hung into hangers from the guide rope or high line and pulled up with a pull rope. Again, to do this we want to avoid deformations too much, and we wanted to avoid the use of tower cranes and things like that. So we used a high line. The completely shop fabricated parallel wire cables come to site on reels, and then they are transported to the site and come out here out of these boxes. The boxes were therefore, during transport they were closed, and that time of the year it was very cold at night. And so the PE pipes, when cold, become brittle, can easily break. So there was some industrial heater in these boxes, and before pulling up they were heated up so that they are smooth and not brittle anymore. So here they go up, this banana as we called it, the cable guide pulled up, and here we see what the picture was. We have the high line, we have the hangers, and we have the actual cable supported by the hangers pulled up, threaded into the passive anchorage in the steel tower heads. Here we have the cable anchor heads resting on crossbars and shims, and on the other hand, at the beam, I showed you the detail, sticking through, sticking out. We like to show the flow of forces so that people can see, aha, that's the cable, that's where it's anchored, and it doesn't disappear somewhere in there. We have here from the top the steel pipe, and here a bell, a boot to cover the hole. Now, for the initial cables, a little tedious way inserting the cement grout for corrosion protection. It was empty. So what we do is we have here a pressure pipe, similar as we grout tendons, a pressure pipe with the grout going, of course, from bottom to top. In order to have a minimum pressure at the top also and not remaining air, we use stand pipes, and we wait until the grout comes out at the tip of the stand pipes. Then we know we have at least 2 meters pressure at the top also to ascertain the grout is tight. And not believing that, we also afterwards cut some windows here in the top of the PE pipe where it's always difficult whether it's filled or not. And we saw, thank God, beautifully filled and everything in good order. However, it's a tedious process. It takes time. It's costly. It can be messy. You know, cement grout spoils over the deck, you have to get it off. And mistakes have been made insofar that the grouting pressure was too high. It's very simple. On one way it's complicated, why? But in the result it's very simple. The pressure must not be bigger, or say the widening of the PE pipe, the strain due to internal grouting pressure, must not be bigger than 2%. Then it works beautifully. We had examples where they over-grouted, overstressed. We had 8% strain, opening, widening of the pipe. And then, of course, the concrete the cement hardens, and the strain is frozen in. And then after 2-3 years, the PE pipes crack. It's a long story. I just want to say there are some shortcomings with this cement grouting. It works beautifully, but tedious. So we used later the petroleum wax. Finally, the coloring. Now, many people say black is beautiful, but some say rather I have some light. So it was decided we want light, near white stay cables. You cannot paint them because PE is chemically inert, träge. No paint sticks to PE, it flakes off. So what we came up with was a tape overlapping 50% which sticks on itself. And this was then used, and we had the beautiful white cables, and that's the completed bridge. That was, I think, 1978. And to the best of my knowledge, nothing happened to it, so the bridge, there were some problems with the tape, but that was overcome. The bridge is still in good shape, and that's how it looks by night with flat light. So it was quite a success. Very briefly now, similar but with some differences, bridge across the Ohio River, West Virginia. You know all the beautiful song which describes West Virginia, and I've been there several times, and it really is a beautiful, beautiful landscape. Now, the speciality was, when we started to design the bridge, the main piers were already cast. Well, how that? There was an initial design for an all-steel cable-stayed bridge. Then, Federal Highway Administration in Washington, D.C. changed its policy. They wanted competitive designs. Now, the contractor will not offer a competitive design because they will not take the risk that the bridge later on serves its intended purpose. They will, if you give them the hammer and the nail and show them the drawing, they will put in the nail, but they will not guarantee that you can hang a picture onto that nail. That's up to you. So it's a legal process in the US. So how to make competitive designs? Well, we make two official designs, one in steel, one in concrete. At that time, for all projects more than $10 million. And this was the first one. So the design of the steel bridge was approved. The piers were built in the first stage, and then we came and were supposed to put on these existing piers a concrete cable-stayed bridge. Well, we did, and that's again, we had a model picture. Here you see it. One used always high gloss wires, so it looks very nice if you photograph it. Basically, that's the main pier, and these two piers were designed. And so we had to squeeze on here something which could be taken by the foundations. In concrete, what we did is, first of all, we used, at that time, not in the US, completely unknown, high-strength concrete, B65. Nothing to it today, but at that time, 1978, unknown. Well, we did it, and we then said also, okay, we use steel cross-girders, and that was acceptable. It was still a mainly concrete alternate, so to say. And of course, we sized down all dimensions to the absolute minimum, and so we could prove it's possible. For the cable anchorage in the tower, we used for the first, and I think last time, overlapping of the cables, like this. You have a core, you overlap, beautiful, no tensile force. Yes, that's beautiful, but until you have the fiddly geometry done, you're not so happy anymore. So we never did it again, but it worked beautifully here with the overlapping cable anchorage. We see here, during construction, the reinforcement cage with the overlapping steel pipes. Again, free cantilevering with precast elements, staying the tower. We had all that. Here we see the stays, and it happened what one should avoid. We had a ship running into this auxiliary stay at the end of construction. Thank God nothing happens, but since then I've never done it again. Stay across the river when a ship can reach it. The danger is just too big. Well, that's the cross-section, rather absolute minimum you needed. And here we had then, instead of the steel dowels, we had profiled the concrete to take the shear. We had the steel cross girder like this to save weight, cast at the end the shear studs, of course not the structural steel. The concrete stops here, and the forces are carried by the shear studs. Since we have, due to the rotational stiffness, a certain fixing of the cross girder, we have tension here from a positive moment, and in order to carry that we used double stock shear studs, which means we welded on top of one the other shear stud, which permits you rather safely to introduce tensile force via shear studs, whereas normally these only take shear, as the name said. Here we see one element, this time not short line casting one against the other, but they were all cast in one long line against one another and taken out. And the installation was the easy one. We used a floating crane, which is of course the least loading on the beam. Makes your construction engineering much simpler. If you may remember, I showed you construction engineering 2 or 3 lectures ago. Starting with a floating crane, that makes life easy. If you have a traveler on the deck, a derrick, you have to tie it back. Complicated. So, there we used a floating crane. Cable installation, similar as we had it, parallel wire cables, introducing the overlapping in the tower head, using these bananas cable guides. Then pulling at the beam, pulling the tie rod with the strand here into the steel pipe to the jack. This is the jack, sitting on a jack chair. That's all there was to get to this dressing, this fiddly staircase here. I've been up and down sometimes, but it was the absolute minimum there. And here we have the completed bridge. Here's, by the way, still the floating crane standing. And it looks very nice, I think, again, with the white cables. Now, construction of cable-stayed bridges with precast element beams. The advantage of precast elements is that you can have very high concrete quality, cast under controlled conditions, can easily build a shed around in adverse weather and so on. High quality. You can do it very precisely. It's worth to make steel forms which keep. You can cast them against one another, match casting, so they fit beautifully, and they did. You can glue the joints with epoxy, so you safely avoid that you have little non-fitting places where the water can run through. It's absolutely watertight. The disadvantage, of course, and you have less shrinkage and creep once they are installed, because they are, say, 1 year in average old. So most of the shrinkage and creep capacity is already gone. Those are the advantages. As always in life, there is no such thing like a free lunch. We also have disadvantage. And that is basically the transport of heavy weight. In this case, 270 tons. To transport that, to install it, requires equipment. So That's the pros and cons. But I have shown you, in this particular case, at that time, was the first cable-stayed bridge in the US, and free cantilevering, all that was not very well known. The contract, we wanted to first do it in cast in place. But the contractors in the US said, no way. 150 meters free cantilevering over the river, cast in place. We have never done it, and we will not do it. Simple. So then we said, okay, and came up with a precast element, and there was then finally outstanding, capable contractor. Martin Kelly was a perfect site manager. Martin Kelly, they did it first time, everything right. So we were forced to use precast elements, but we did our best and it worked. East Huntington then was a little bit easier because instead of lifting the heavy element from the beam, we used a floating crane, but otherwise very similar, and both bridges worked well, and to the best of my knowledge have not shown any signs of deterioration. So it can be done. Next time we will see then cast in place and all the other methods. Thank you very much.